What is the age of our universe? This question has puzzled scientists for centuries. Although it seemed like a simple question, over time it has become apparent that finding the answer is not so simple. Today, this question continues to be debated as new research constantly challenges our understanding of the age of the billions of galaxies that make up our universe. A week ago, a groundbreaking study based on data from the James Webb Space Telescope challenged the widely accepted notion that our universe is approximately 13.8 billion years old. The study suggests that the universe could be twice as old, which would break the cosmological model and solve the enigmatic and complex problems of the first galaxies. But is this really possible? Join us on this journey because we are going to dive into the immensity of the cosmos to analyze this discovery. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel. Be sure to like this video, share it so it reaches more people, and activate the notification bell. It is important to note that one of the most revealing facts about the universe is that we know its age, 13.8 billion years. However, this figure is being questioned and reevaluated based on exciting new research. If we were to go back in time, we would discover that the early universe was very different from how we know it now. The stars and galaxies we observe today arose through gravitational mergers of objects consisting of younger, pristine stars. In those initial moments, no stars or galaxies existed. If we continue to look into the past, we would arrive at the moment of the Big Bang, which marks the beginning of the universe as we know it today. Today, astronomers and astrophysicists studying the early universe claim to have estimated its age with an uncertainty of less than 1%. A remarkable achievement that represents the discovery of the universe's birthday. To measure the age of the universe, there are two methods compatible with this figure. The first is by tracing the history of the universe, a powerful way to estimate its age. This method is based on the discovery of the expansion of the universe in the 1920s. In physics, if you know the equations governing the system and you know how it evolves in time, you can go back into the past or forward into the future as long as the laws of physics and the content of the systems do not change. In the field of astrophysics and cosmology, the laws governing the expansion of the universe arise by solving the theory of general relativity for a universe that, on average, is filled with equal amount of stuff everywhere and in all directions. We call this homogeneous, equal everywhere, and isotropic, equal in all directions universe. The consequences of this resolution are known as the Friedmann equations, after Alexander Friedmann, who was the first to derive them 99 years ago in 1922. These equations tell us that a universe full of stuff must expand or contract in a particular way. The rate of expansion or contraction changes with time and depends only on two factors. First, the rate of expansion at any point in the present, and second, what kind of content the universe has at that specific point. In the early days of cosmology, they used to joke that cosmology was the search for two numbers, implying that if we could measure the expansion rate and how it changes with time, we will have the information we need. Currently, we know those two numbers, the Hubble parameter, which represents the current expansion rate of the universe, and the deceleration parameter, which is its negative, meaning that the universe is not slowing down as previously thought, but is accelerating its expansion. If we could accurately determine the expansion rate of the universe, we would be able to know in detail the composition of the universe. That is, we could know about the normal matter, dark matter, radiation, neutrinos, dark energy, and other components that are present. We could also go back in time to the initial moments of the Big Bang, where the universe was very hot, dense, and occupied a small volume. The amount of time we take to go back to that point gives us the age of the universe. The study published in July 7th in the journal Monthly Notices of the Royal Astronomical Society appears to confirm that previously estimates of the age of the universe were significantly wrong. This new study addresses what is called the impossible problem of the first galaxies, which has long puzzled scientists. According to the study, some galaxies that were thought to have existed shortly after the Big Bang actually appear to be much older than previously estimated. Observations made with the James Webb Space Telescope showed that galaxies and stars like Methuselah appear to have a level of mass maturity normally associated with billions of years of evolution. This is surprising considering that it was believed that these galaxies formed hundreds of millions of years after the Big Bang. An assistant professor of physics at the University of Ottawa suggests that these puzzling observations can be explained by the fact that our universe is actually much older than previously thought. The professor's study presents a new model that extends the time of the galaxy formation by several billion years, giving the universe an age of 26.7 billion years, twice what is generally accepted. This model incorporates Fritz Zwicky's tired light theory, which suggests that the observed redshift in the light from the distant galaxies is due to a gradual loss of energy over large cosmic distances. According to the tired light theory proposed by Zwicky, light becomes weaker or tired as it travels great distances through the cosmos. This idea contrasts with the current established theory, which holds that the redshift observed in objects such as galaxies is mainly due to their moving away from us as a result of the expansion of the universe in all directions. The tired light theory has generated significant controversy within the scientific community. Astronomers debated whether the loss of light energy over cosmic distances would not only cause a redshift, but also a decrease in the intensity and brightness of light. Critics argued that if this were true, distant objects could appear much dimmer than actually observed. Furthermore, this theory proposed by Zwicky in the mid-20th century conflicted with the discovery of the cosmic microwave background radiation, which is an uniform radiation present throughout the sky and represents the residual energy of the Big Bang. This radiation provided strong evidence in favor of the expanding universe theory. Although Zwicky's theory was initially found to be in conflict with observations, a new perspective is proposed that allows the tired light theory to coexist with the expanding universe model. According to this new interpretation, the redshift phenomenon can be viewed as a hybrid phenomena that combines both the expansion of the universe and the gradual loss of energy of light during its cosmic journey. This new interpretation offers a credible explanation for the first observations of galaxies, in addition to considering the theory of tired light. It also introduces the concept of blocking constants, an idea proposed by physicist Paul Dirac. These blocking constants are fundamental physical parameters that cause particles interactions, and it is suggested that they may have varied over time. By taking into account the evolution of these blocking constants, the proposed new model extends the time frame for the formation of the first galaxies observed through the James Webb Space Telescope. Instead of just a few 100 million years, this new time frame allows spanning several billion years of cosmic evolution, providing a satisfactory explanation for the development and mass of these ancient galaxies. This model also challenges the radiation interpretation of the cosmological constant, which represents the dark energy responsible for the accelerating expansion of the universe. Instead, a modified constant is proposed that takes into account the evolution of the constraining constants. This modification in the cosmological model may help solve the puzzling puzzle of the small size of galaxies observed in the early universe and provide a more accurate picture of cosmic evolution. What do you think? Do you think we've been wrong all this time? Let us know in the comments box. If you liked the video, remember to hit the like button and subscribe to the channel so you don't miss out on more content like this. Thank you very much for watching the video, and I'll see you in the next one around.